Okay, let's do the review for Chapter 10. It's found on page 323. Define the following terms. A, Boyle's law. Boyle's law is at a constant temperature, pressure and volume are inversely proportional. Charles' law is when the pressure is held constant, the temperature and volume are directly proportional. Extrapolation is when you extend data out, the trend, where there's no measurements. So you're extending the data out, following a trend, but past where there are measurements. That's extrapolation. D, Avogadro's law. Equal volumes of all gases at the same temperature and pressure have the same number of moles. And E, boiling point. It's the temperature at which liquids' vapor pressure is equal to the external air pressure. Number 2, what is a Pascal? A Pascal is a Newton per meter squared. A Pascal equals Newton over meter squared. For your test, remember that a Pascal, an atmosphere, torr, millimeter of mercury are all standard units of pressure. Did you get that? Standard units of pressure would be a Pascal, atmosphere, torr, millimeters of mercury. Those are all standard pressure units that are used. What is what does a barometer measure? It measures pressure. Number 4, why are inches of mercury and millimeters of mercury used as units for pressure? Because the height of the column would be too great. Mercury is very heavy, and so that keeps the height of the column down to a more reasonable roar, or length, I should say. Number 5, if you put an inflated balloon into a container and then add lots more pressure to the container without changing the temperature, what will happen to the size of the balloon? It will decrease. If you're increasing the pressure, you're going to decrease the size of the balloon. Number 6, if you inflate a balloon at room temperature and then put it in a freezer that is at the same pressure, what will happen to the size of the balloon? Once again, because the molecules will be drawn closer together because the lower temperature, it will get smaller. It will decrease in size. Number 7, what does it mean for temperature scale to be an absolute temperature scale? That means you can't reach 0. That's why it's an absolute temperature scale. Number 8, and remember that's important when we work on the gas chapter because you have temperatures in the denominator a lot. So you can't have a 0. That's why we have to use the other scale. Number 8, what is the boiling point of water at 1 atmosphere in Kelvin? Well, remember, the boiling point of water is 100 degrees Celsius. You all should have that memorized. And to convert to Kelvin, you add 273.15. And remember, this has an infinite number of significant figures. So the boiling point of water in Kelvin would be 373.15 Kelvin. It's not degrees, it's just Kelvin. Number 9, nitrogen condenses at 77 Kelvin. What is the temperature in degrees Celsius? Once again, the conversion between those, 77 Kelvin minus 273.15, will give you negative 196. It actually gives you digits out here, but you can only go to the ones place, and so that's going to be your answer in Celsius. So remember, this is the difference between them, the 273.15. And hopefully you have that memorized by now by doing all the conversions in the chapter. Okay, number 10. When extrapolating, a good scientist keeps the range of extrapolation blank compared to the range over which the data have been measured. That should be small. Your extrapolation should be small compared to the amount of data that you have measured. Number 11. Why must you use an absolute temperature scale like the Kelvin scale when working with the gas laws? Because otherwise you'd end up with zeros in the denominator, and you can't do that. It's undefined. The math police will come out and get you, woo, 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 and they'll take you away. Anyway, okay. You needed that, didn't you? I did. Number 12, a piston contains 45.6 mils of gas at a pressure of 814 torr. If the temperature doesn't change, what is the volume of the gas at a pressure of 760 torr? Okay, so here we are looking at V1 P1 over T1 equals V2 P2 over T2. And in this particular one, okay, the piston contains 45.6 mils of gas at a pressure of 814 torr. And so if the temperature doesn't change, so we're going to leave these out. What is the volume of gas at a pressure of, okay, so and that's in torr. So that's good. So the first one, I'm going to go ahead and put them in mils. 45.6 mils. And the starting pressure is 814 torr. And then equals we're looking for the secondary volume. So I'll put volume here. And then the torr is 760. Much different. Yep, different on the significant figures. There we go. So you just do this divided by this. The torr will cancel. I'll show you. We divide both sides by the 760 torr. And I do it over here too, so it leaves. And so we have 3 significant figures, and so that's going to limit our answer. And so our answer is going to be 48.8 mils, because torr will leave and I'll be left with mils. So my answer is in mils. Got to work carefully so you don't put the things in the wrong places. That's what I do. So you got to work carefully on that. Let's see. Next one. 13, a flexible container is held at a constant pressure. So the pressure is constant. I guess I should just leave this up here, shouldn't I? V1 P1 over T1 equals V2 P2 over T2. Okay. And we're holding pressure constant, so that's going to leave this time. It starts with the volume of 1.2 liters and a temperature of 25 degrees Celsius, but we can't use that, so we're going to go plus 273.15 equals, and that's going to give me 298.2 Kelvin. So I'm going to put that in, 298.2 Kelvin. And then, let's see, what is the new volume? So what is the volume if the temperature is 50 degrees? So we're going to go 50 degrees Celsius, and I've got the right number of significant figures, yes, plus 273.15 equals 323.2 Kelvin. Just want to check, yes, 323.2 Kelvin. Once again, we're going to multiply that to this side. You're going to have an answer in 2 significant figures. So your answer is going to be 1.3. Kelvin's going to leave. You're going to be left with liters. So the volume is 1.3 liters. Number 14. A helium-filled balloon has a volume of that at an altitude where the temperature is 0 and the pressure is that. It is brought back to the ground where the temperature is the new temperature and the volume is 21.1 liters. What is the pressure on the ground? Okay, so once again, we have V1 P1 over T1 equals V2 P2 over T2. And so now we're going to use all of them. The volume is 35.4 liters. Has an altitude where the temperature is 0 degrees Celsius, and so I'm going to add my 273.15, and that's going to give me my Kelvin. And the pressure is in atmospheres, 0.619 atmospheres. Okay, there's my first set of data. It's brought back to the ground where the temperature is. Okay, now we need T2. Now we're given 22.90 degrees Celsius, 273.15. So that's going to give me 501,692. Yes, I can use all of those significant figures here. So that's 296.05. And that's going over here. 296.05 Kelvin. Okay. Go back to the ground where temperature is that. Its volume is 21.1 liters. What is the pressure? That's what we're solving for. And so you would go ahead and do that. Looks like you have 3 significant figures. So your answer is going to be in 3 significant figures, 1.13 atmospheres. Because when you do this, the Kelvin will cancel because this is going to go up there. So the Kelvin will cancel. This will come down here. So the liters will cancel. You'll be left with atmospheres. And so there's your atmospheres. Make sure you don't put the Kelvin in any of these temperatures. That's a no-no. Got to use Kelvin in anything to do with gases. 15, in each case, indicate which of the 2 situations will be most likely to produce ideal behavior in a gas. And I've written up here for you that it behaves ideally when the temperature is greater than or equal to 0 degrees Celsius, which remember is 273.15 Kelvin, just so you can remember. And the pressure is less than 1 atmosphere. Remember, 1 atmosphere is the same as 760 torr, or 760 millimeters of mercury. Okay, so let's apply that. So the first one, A, the temperature is 124 Kelvin, and so that is less than this. So that's not going to behave ideally. Look at the second one. The second one is 280 degrees Kelvin, that fits this parameter, and 1 atmosphere, that fits this. So circle number 2 for A. B, the first one is 273 Kelvin, so that fits this parameter, and 760 torr, which means the pressure is less than 1 atmosphere. So that one works. So you could circle that one. Look at the second one, 275. That fits, but whoa, really high pressure. That doesn't fit. So it's definitely on B. It's the first one. And then C, you have STP, which is 0 Celsius or 273, and 1 atmosphere. So that fits. The second one, the temperature is really, really low. And the pressure is really, really high. So on C, it's definitely going to be the first one. So what you have to memorize, though, is that this is when a gas acts ideally, when the temperature is basically above the freezing point of water and when the atmospheric pressure, the pressure is below 1 atmosphere. And you kind of have to have a feel for what things equal that to be able to answer those questions. Number 16, how many moles of nitrogen are present in 891 ml container at 23 degrees Celsius and 345 torr? Here we're going to use PV equals nRT because it asked you for moles. So you know you're going to use the ideal gas law. PV equals N, and I'm just going to put N, don't make it fancy, nRT. All right, so we want to solve for moles because that's what we're being asked for. And so we are given that the pressure is 300, let's see, is R is in atmospheres, so I'm not going to put the torrs in there. It gave us 345 torr for the pressure, but when I put R in here, R is going to be 0.0821 liters, atmospheres, moles Kelvin. So I have to have my pressure up here in atmospheres. So I'm going to go like this, and I know that there are 760 torr in every 1 atmosphere. And so that's going to end up giving me 0.454 atmospheres. That's what 345 torr are. So I'm going to go back over here and go 0.454 atmospheres. Now I'm going to ditch that. The volume that we're given, this is in liters, and it's given to me in milliliters, so I'm going to bring the decimal back 3 places to make it liters. So I'm going to put it 0.891 liters. And now the temperature needs to be in Kelvin as always. We're given the temperature as 23.0 degrees Celsius. We go 273.15. That's going to give me 296.2 with the right number of significant figures. 296.2 Kelvin. There we go. Now we have all of it in there. And the atmospheres should cancel, the liters should cancel, the Kelvin should cancel, and we'll be left with moles. We have 3 significant figures. That has 4, but most of them have 3. So our answer will be 0.0166 moles. Whew! Got to be careful when you put these in, and this limits what your units can be. So make sure that your units cancel where they should, and that caused us to take the torr that they gave us and convert this into liters. And then, as always, we're converting the Celsius into Kelvin. And the reason they do that is because our thermometers don't read Kelvin. Our thermometers read Celsius. So it's always going to be that we have to do that conversion. I'm just really thankful. It's a really easy conversion. So that's a good thing. Number 17, what is the volume of 10 grams of water vapor at 134.5 degrees Celsius and a pressure of 567 torr? So we are looking for the volume. And once again, we're going to use PV equals nRT. And so we have, what is the volume? We're looking for volume. So I'm going to go ahead and solve for volume. It says, what is the volume of 10 grams of water vapor? So to get the moles, I'm going to have to go 10 grams water times line, grams of water, moles of water. 1 mole, 18.02 grams. And that's going to give me 0.3 significant figures, 555 moles of water. I'm sure you can hear it, but it's raining cats and dogs outside. So I guess this is a safe place to be in the church. So I'm going to put that in, 0.555 moles of water. Okay, R is given to us, so that is 0.0821, and that is liters, atmospheres, moles, Kelvin. And then the temperature, we're told, woohoo, temperature is high. I'm going to make some room here. Temperature is 134.5 degrees Celsius plus 273.15, so that's going to give me, wow. Now, we can only use it, though, to this place, so this is going to roll up. So we're going to go 407.7 Kelvin. Okay, now for the pressure. It's got to be in atmospheres, and it's given to us here in torr. 567 torr. Got to be in atmospheres because of R times line. Torr, atmospheres, 760. So that's going to end up in 3 significant figures, 0.745 6 atmospheres. Whew, there it all is. Let's see, 3 significant figures, 3. So it's going to be limited to 3 significant figures. Atmospheres will cancel. Moles will cancel. Kelvin will cancel, so we'll be left with liters, which is what we were looking for. That's good. And so in 3 significant figures, it's going to end up being 24.9 liters. Hey, number 18, in the following decomposition of 150 grams of potassium chlorate, what volume of oxygen is made at STP? Wow. This is really using a lot of the different skills that you've learned this year. So let's do this. We're doing a decomposition reaction. I know, aren't you excited? We're doing a decomposition reaction. So we have potassium chlorate. Remember, we take it down to its elemental form. We ask who gets the little 2's, H, N, O, and the first 4 in group 7, which this is one of them. Okay, those get the little 2's. I can see here I'm going to need to go to 6 as my lowest common multiple. So I'm going to go 3 here and 2 here. That gives me a 2 here and a, whoops, that's already got a 2. Sorry, I'm in good shape, aren't I? So 2 potassiums, 2 potassiums, 2 chlorides, 2 chlorides, 6 oxygens. Good, so far so good. Let's go back to the problem. We have the decomposition. We have 150 grams being decomposed. 150 grams. What volume of oxygen is made at STP? Wants to know the volume. So I'm going to put liters there. What volume of oxygen is made at STP? Now, what is the only way we have to get from here to here? Moles. I don't care what he's asking for. You got to use moles to get from one place to the other in a balanced chemical equation. So we're going to go to moles first. So we go 150.0 grams of potassium chlorate times line. The grams of potassium chlorate to the moles. And we're going to add that bad boy up, and it's going to be 122.55. That's going, well, let's see. Let's go over to the moles of this guy. Okay, so now we go moles to the moles O2, because this is where we're trying to go, right? 2 equals 4 significant figures, 1.837 moles of O2. He's got 1.836. Let me take it one step at a time. 122. 122.4. Yeah, his is 6. So I'm just going to put a 6 there so I don't confuse you. Okay, so that's my moles. Now, our question was, what is the volume of oxygen made at STP? The volume of oxygen. Now we have to use, I'll put it down here. PV equals nRT. Because we're looking for volume, aren't we? And we have moles. So, and we also have STP. So let's solve for volume. So we're going to go like this. And so the moles we're going to plug in as 1.836 moles of O2. And this is important. You don't stop here with the moles of this, because this isn't the gas. This is the one they're asking about. You had to go through the mole tunnel to get to the moles of O2. That's why it was important to lay it out. R we know is 0.0821. Okay. The temperature, it's at STP, so that's 0 degrees Celsius, so 273.15 Kelvin. And the pressure is at 1 atmosphere because it's at STP. So here, Kelvin will cancel, atmospheres will cancel, moles will cancel, and you'll be left with liters. We have 3 significant figures every place. And so our answer should be, I'm going to put it up here, 41.2 liters. 41.2 liters after you do all that. Okay, number 19. A chemist burns 567 liters of propane. How many liters of carbon dioxide are made? And then he gives the information. Okay, so let's try this. Oh, and we have the equation right below that. So we have propane is C3H8 plus ... We're trying to get information on carbon dioxide. Okay, we have 567 liters of this. How many liters of carbon dioxide are made? Question mark, liters. Okay, so we have to get, these are both gases. I should have written that, but I didn't. And that means we can go through the mole bridge for that. So we should go liters of the C3H8 times line, liters of C3H8 to liters of CO2, 3, 1. And so that's going to give us, in 3 significant figures, what I get in my calculator is 1701, but I need that in 3 significant figures. So the best way would probably be to go like this. 1, 2, 3. And that would be liters of CO2. So that would be your answer. Now this one, there's not a lot of work involved. You could have expressed it this way if you chose to. Don't leave that. You just had to remember that for gases, it works like moles. You can go back and forth between the volumes, but only for gases. 20. A balloon is filled with 345 torr of oxygen gas and 14 torr of nitrogen gas. What is the mole fraction of each gas? Okay. So, we filled with 345 torr of oxygen gas, 345 torr, and that is the pressure of oxygen gas. And then nitrogen gas, the pressure is 416 torr. What is the mole fraction? Well, remember, the mole fraction is the fraction of this one divided by the total. So first we need to get the total. In other words, the mole fraction, we need to get, that's going to give us the fraction, right? And so the total here, when you add these two up, is 761 torr. So if we want the fraction of oxygen, we would go 345 torr divided by 761 torr. 3 significant figures each. It's going to give us 0.453. And then for nitrogen, we're going to go 416 torr divided by 761 torr. And that gives us 0.547. And for this one, it just asked the mole fraction for each gas, so you're done. That's all you had to do. Number 21. A container holds 0.34 moles of chlorine gas, 0.22 moles of xenon gas, and 0.56 moles of krypton gas. If the total pressure of the gases is 1.1 atmospheres, what is the partial pressure of each gas? Excuse me. All right, remember that the mole fraction of any particular gas, we just saw that, equals the partial pressure of that gas over the total pressure of that gas, right? And we're trying to find the partial pressure of the gases, and we're given the number of moles, and so we need to find partial pressure of each gas. We're trying to find this. So to find the partial pressure of each gas, we're going to need the mole fraction, and the total pressure we can find by just, it's right there given to us. The total pressure is 1.1 atmospheres. So this is given, and we're looking for this, so we have to find the mole fraction. Now, to find the mole fraction, all we're going to do is add up the number of moles, and so we have 0.34 moles of chlorine gas. We have 0.22 moles of xenon gas. Just let me look. No, okay. And then we have 0.56 moles of krypton gas. KR, there it is. Okay, KR. There we go. So to find the mole fraction, you'd get the total because it'd just be this divided by the total will give you the mole fraction. Very easy stuff. And so if you add these up, which I'm sure I've done here somewhere, there it is. It ends up being 1.12 moles. That's the total number of moles. So now for the mole fraction for this one, I would go 0.34 divided by 1.12, these are both moles. And that's going to give me the mole fraction for chlorine, which is 0.30. And then when I do this one, divided by 1.12, it's going to give me the mole fraction. I'm going to go ahead and put here, this is the mole fraction for chlorine gas. The mole fraction for xenon gas is going to be 0.20, and the mole fraction for krypton gas is going to be 0.50. Now that we have that, we can go back over here and figure out the partial pressures of each of these gases, because we know that the partial pressure of the chlorine gas equals the mole fraction, which is 0.30, times the total, which we're given in the problem as 1.1 atmospheres. The partial pressure for the xenon gas is going to be, that's mole fraction, times 1.1 atmosphere. And the partial pressure for krypton gas is going to be 0.50 times the partial pressure, the total pressure for that gas. And so then we have two significant figures in each of those. 0.3 times 1.1 is 0.33 atmospheres. 0.2 times 1.1 is 0.22 atmospheres. 0.5 times 1.1 equals 0.55 atmospheres. Good. And if you add those all up, you get 1.1 atmospheres. So that's a good thing. So there's your answers. The partial pressure of the xenon gas is 0.22 atmospheres. The partial pressure of the krypton gas is 0.55. And the partial pressure of the chlorine gas is 0.33. So there you have it. 22. A camper boils water to cook dinner. He cooks the same dinner 2 nights in a row, but it takes longer for the same amount of the same dinner to cook on the second night. Compare the atmospheric pressure he experiences on the 2 nights. Well, because the water boiled at a lower temperature, it took longer to cook. Therefore, the pressure was lower on the second night. So if the water boiled at a lower temperature because of a reduced pressure, then it would take longer for it to cook. Think of how a pressure cooker works. It actually increases the pressure, therefore the temperature has to increase, and so the food cooks much more quickly. That's how that works. Number 23, a chemist makes hydrogen gas according to the equation, and that below. She collects the hydrogen gas over water in which the reaction is taking place. If she collects that volume at that pressure and that temperature, how many moles of gas did she make? Well, we are going to use the ideal gas law for that because we have the moles involved. PV equals nRT. We're solving for moles here, so we're going to have PV over RT, aren't we? Now, we can't just plug in the pressure because she's done this over water. So the water vapor is involved. So we're going to go back to page 311, and we see that at this temperature, 60 degrees, the water vapor pressure, the vapor pressure, I can talk, the vapor pressure for water is 149.4. And so that is the, I'm going to put it here for right now, the partial pressure of the water. Now remember, we're looking for the pressure of the hydrogen gas. And the pressure total, which is given to us, equals the pressure of the hydrogen gas plus the pressure of the water. And the pressure that we were given was the total. We need this pressure, don't we? Okay, that's why we're going through this. Because we can't just stick this pressure in here. That would be the total pressure, and it would include the water, and we don't need that. We are being asked for the hydrogen, so we have to find this partial pressure. So we go over to the chart, we look at 60 degrees, and the partial pressure of water at 60 degrees is 149.4 torr. But you and I both know that R is given in atmospheres, not torr. So we're going to have to convert this to atmospheres. And so that's going to give us 0.1966 atmospheres. Now we have the information we need to find this, because to find that, right, I just solved for this one. So the pressure that was given to us, the total pressure is 0.981 atmospheres minus, this is the partial pressure of the water that it was collected over. And so that's going to give us a partial pressure for the water of 0.784 atmospheres. There we go. So now that we have the pressure, I can come back over here. I'm going to ditch this. I'm going to put this pressure in. 0.784 atmospheres. So far, so good. We are given the volume at 3.41 liters. We know R is 0.0821 liters atmospheres per mole Kelvin. And we're given the temperature at 60 degrees Celsius, but we know we're going to go 273.15, and that's going to give 13.3. And this has got to go to here, so we're going to put this in as 333.2 Kelvin. There we go. And so, poor calculator. Once you have all that, the moles will actually be left. The Kelvin goes, the liters go, the atmospheres go, the moles is what's left. And we have 3 significant figures and 4, so we're going to answer in 3. So it's going to be 0.3 0.0977 moles of hydrogen gas. The tricky part was the pressure. You couldn't just stuff in the pressure because that was the total pressure. And we knew that because it mentioned to us that the hydrogen was collected over water. So we knew we had to take a partial pressure there to find the partial pressure of the hydrogen and put that in. And then everything else was fairly straightforward. Okay. You need to make sure you're good with this and then go ahead and take your test for Chapter 10. And I'll see you in class.